In Chapter 11, we discuss mixed strategy Nash equilibria. And so this follows Watson's text, Strategy, an Introduction to Game Theory. In some games, there are no pure strategy Nash equilibria, and in such cases, if we have a finite strategy set for players, there must be a mixed strategy Nash equilibrium. So if we have a finite set of strategies for each player, and there are no pure strategy Nash equilibria, then John Nash proved that there must be a Nash equilibrium in mixed strategies. A mixed strategy profile is one in which each player plays a set of pure strategies according to a certain probability distribution that they've chosen. If there is more than one pure strategy Nash equilibrium, there can also be mixed strategy Nash equilibria. You might mix between your strategies that support different pure strategy Nash equilibria. So usually in these finite choice set games, finite strategy set games, we look for mixed strategy Nash equilibria when there are no pure strategy Nash equilibria, or when there is more than one pure strategy Nash equilibrium. So let us consider a baseball pitcher who can throw a fastball or a breaking ball. The batter simultaneously chooses to swing for fastball or to swing for breaking ball. So this is a game between a pitcher and a batter in baseball, where the strategy, the set of possible strategies for the pitcher are fastball or breaking ball. And the set of possible strategies for the batter are swing for fastball, swing for breaking ball. And you can do a best response analysis, and you can find there are no cells in which all arrows are toward. In other words, there are no pure strategy Nash equilibria in this game. So we know from Nash to look for a mixed strategy Nash equilibrium of this game. And you can verify for yourself. You can draw up the game, verify for yourself that there are no pure strategy Nash equilibria in this game. And there's a reason for that. Essentially, the pitcher doesn't want to pitch fastball all the time. Then the batter would know that the pitcher was going to pitch fastball, and the batter would always swing for fastball, and the batter would get a hit 40% of the time, which is really high in baseball. Okay? So, and if the pitcher pitched always pitched breaking ball, then the batter would know to swing for breaking ball, and the batter would get a hit 40% of the time again. And so you don't want to be predictable in a game like this. Similarly, the batter doesn't want to always swing for fastball. They're always going, if they always swing for a fastball, they're always going to get a breaking ball pitched to them from the pitcher, and they're only going to get hit 10% of the time. Okay? And then similarly, if the batter always swings for breaking ball, then they're always going to see a fastball from the pitcher, and they're only going to get a hit, again, 10% of the time. So this is a bad game in which to be predictable from either side, and you don't want to get stuck in a pattern. You don't want to always do the same thing. That's a pattern. And you don't want to get stuck in a pattern like fastball, breaking ball, fastball, breaking ball. The pitcher doesn't want to alternate. You want to randomize according to a probability distribution. So a mixed strategy Nash equilibrium implies that you're mixing according to a probability distribution, and from trial to trial, from pitch to pitch, in this case, you're mixing randomly. So, which means you're just independently drawing from pitch to pitch from this distribution. So, if you pitch a fastball 50% of the time, then on every pitch, there's a 50% chance that you would pitch a fastball. So again, there are no pure strategy Nash equilibria in this case. So there must be a Nash equilibrium in pure strategies. So how do we calculate a mixed strategy Nash equilibrium? Well, in a mixed strategy Nash equilibrium, each player chooses a probability distribution Okay, so player 1 chooses sigma 1, which is just a probability distribution, p and 1 minus p. P meaning the probability that they choose fastball in a given pitch. 1 minus p is the probability in this case of breaking ball. Player 2 chooses sigma 2, which is a probability distribution on their swing timing. Q means the probability that they swing for a fastball. 1 minus Q is the probability they swing for a breaking ball. Okay, so essentially, when you choose a mixed strategy Nash equilibrium, you're choosing these probability distributions. Each player is choosing an optimal probability distribution. Okay, so we really have to think about what a mixed strategy Nash equilibrium is and what it does. In equilibrium, in a mixed strategy Nash equilibrium, P and Q are chosen by the respective players, players 1 and 2, to make the other player indifferent between their available pure strategies. In this case, what that means is that sigma star for the pitcher's mixed strategy profile, you can also call this P star, comma 1 minus P star. It's just their distribution of fastballs and breaking balls. This is chosen such that the batter will get the same payoff. The utility to the batter is the same when the batter swings fastball and when the batter swings breaking ball. So given sigma star is chosen by the pitcher, the utility of the batter or the payoff of the batter is the same when they swing fastball as when they swing breaking ball. So that's what that first equation says. Okay, so essentially the pitcher has chosen P star and 1 minus P star to make the batter indifferent on the margin between swinging fastball and swinging breaking ball. And that makes a lot of sense. If there's an advantage for the batter choosing to swing fastball, then that means maybe the pitcher's throwing too many fastballs. Okay, they're leaving an advantage for the batter because they're throwing too many fastballs or they're throwing them in a very patterned way. But essentially on any given pitch that the batter sees, they should be indifferent between swinging fastball and swinging breaking ball if P star and 1 minus P star support a mixed strategy Nash equilibrium. And this goes the other way. The mixed strategy profile chosen by the batter, if it supports a mixed strategy Nash equilibrium, it should make the pitcher's payoff the same whether the pitcher chooses to throw a fastball or to throw a breaking ball. Okay, so the payoff to the pitcher given Q star should be the same whether the pitcher throws fastball or the pitcher throws breaking ball. That's the second equilibrium condition equation on this slide. And we'll see how to incorporate these two conditions when we solve the game between the pitcher and the batter for a mixed strategy Nash equilibrium. And we'll do that in the next slide. To find P star Q star, or our mixed strategy Nash equilibrium, we create an extra column and row in our normal form. We call the extra row the P mix row, the extra column the Q mix column. So what the P mix row has in it are payoffs to the batter should the pitcher employ a mixed strategy where the pitcher is pitching fastball with probability P, breaking ball with probability 1 minus P. So it's the payoff to the batter. That first entry in the P mix row is the payoff to the batter should the pitcher follow the designated mixed strategy and the batter swing for fastball. Okay, so if this happens, you can kind of follow the reasoning by which we get this payoff by just moving down the first column. Okay, so if the batter chooses to swing fastball and the pitcher is pitching fastball with probability P, breaking ball with probability 1 minus P, then the payoff to the batter is going to be 40P plus 10 times 1 minus P. Okay, so we're moving down that first column. We're looking at second payoffs. Okay, moving down the first column because the the batter is using, under this payoff, the batter is definitely swinging for fastball. Okay, so if the batter swings for fastball, then with probability P, they're going to be pitched a fastball, and they're going to get a payoff of 40 or hit the ball with probability 40%. Okay, so the payoff to the batter is going, in this case, is going to be 40 times P, because they're going to guess right with probability P, and they're going to get a payoff of 40 plus 10 times 1 minus P. Okay, so if the batter swings for fastball and the pitcher pitches a breaking ball, so the pitcher is going to pitch a breaking ball with probability 1 minus P, and under this case, the batter gets a payoff of 10, or hits the ball with probability 10%. Okay, so that's how we get the payoff to the batter. Should the batter swing fastball and the pitcher choose a fastball with probability P, a breaking ball with probability 1 minus P, that payoff to the batter is 40P plus 10 times 1 minus P. Okay, moving across the P mix row to that second entry, the payoff to the batter, should the pitcher follow the designated mix strategy and the batter swing for a breaking ball, is going to be 10 times P plus 40 times 1 minus P. Okay, so again, looking down now the second column and looking at second payoffs for the batter, well, if the batter swings for breaking ball, then they're going to get a payoff of 10 when the pitcher pitches a fastball. So the pitcher pitches a fastball with probability P. So they're going to get a payoff of 10 with probability P, plus a payoff of 40 with probability 1 minus P. Because if they swing for breaking ball and the pitch is a breaking ball, which happens with probability 1 minus P, they're going to get a payoff of 40 as the batter. Okay, so we have these two expected payoffs to the batter for swinging fastball and swinging breaking ball. And remember, under a mixed strategy Nash equilibrium, the payoffs to the batter should be equal. For the equilibrium value of P chosen by the pitcher, the payoffs to the batter for their two mixed strategies in this case should be equal. So we just set those expected payoffs, those two expected payoffs to the batter in the P mix row, we set them equal to find the equilibrium value of P. Okay, and we're going to do the same thing in the Q mix column. Okay, in the Q mix column, we're trying to find what choices of Q by the batter make the pitcher indifferent between their pure strategies, pitch a fastball and pitch a breaking ball. So moving down the Q mix column, we have that first entry is the payoff to the pitcher should the pitcher pitch a fastball and the batter use a mixed strategy where they swing for fastball with probability Q, swing for breaking ball with probability 1 minus Q. So we're going to get at this expected value, we're going to move along the first row, because the pitcher is definitely, under this payoff, definitely pitching fastball. So we move along the first row, and we're thinking about payoffs to the pitcher. So first payoffs, given the probabilities of the batter swinging fastball and swinging breaking ball under the batter's mixed strategy. Okay, so the payoff to the pitcher, if the pitcher pitches fastball and the batter follows the designated mixed strategy is going to be 60 times Q plus 90 times 1 minus Q. Okay, so if the pitcher pitches fastball, batter follows the mixed strategy, then with probability Q, the pitcher is going to get a payoff of 60, and with probability 1 minus Q, the pitcher is going to get a payoff of 90. Okay, and then we move down the Q mix column, and so that second entry is the payoff to the pitcher should the pitcher choose a breaking ball and the batter choose the designated mixed strategy. Okay, so if the pitcher chooses a breaking ball and the batter is mixing according to Q, 1 minus Q, then with probability Q, the pitcher is going to get a payoff of 90. Okay, we're looking at first payoffs. We're moving across the second row. With probability Q, the pitcher is going to get a payoff of 90. With probability 1 minus Q, the pitcher is going to get a payoff of 60. So the second payoff for the pitcher, should the pitcher choose to pitch breaking ball, is going to be 90 Q plus 60 times 1 minus Q. So in equilibrium, the batter is going to choose Q such that the pitcher's two expected payoffs down the Q mix column are going to be equal. Okay, so now all we have to do to find P star and Q star is to move across the P mix column and set payoffs equal and solve for P, and then we move down along the Q mix column and set expected payoffs equal and then solve for Q. So then the question is, which P star makes the batter indifferent? Which choice of P star by the pitcher makes the batter indifferent between their two pure strategies? Okay, so all we do here is we move really along the P mix row of the previous slide, and we set the payoff to the batter should the batter choose to swing for fastball, given the mixed strategy of the pitcher, equal to the payoff to the batter should the batter choose to swing breaking ball, given that same probability distribution, that same mixed strategy by the pitcher, where the pitcher is pitching fastball with probability P, breaking ball with probability 1 minus P. And we set that equal, then we solve for the P that makes the batter indifferent between swinging fastball and swinging breaking ball. Okay, and this exercise leads us to the front end of a mixed strategy Nash equilibrium, where we get the mixing distribution of the pitcher as P star equals 1/2, 1 minus P star equals 1/2. So they're going to throw fastball half the time, breaking ball half the time. We still don't know what the batter is going to do, so we have to solve the Q mix column for that. So the back end of the Nash equilibrium is the Q mix column. Which Q star makes the pitcher indifferent between the pitcher's pure strategy choices? So really we want to set the pitcher's payoffs along the Q mix column for choosing fastball and breaking ball, given the mixed strategy distribution of the batter, Q and 1 minus Q. We want to set these payoffs for the pitcher equal, and we want to solve for Q star. So if we do that, we get that Q star is also equal to 1/2, and 1 minus Q star equals 1/2. So in this mixed strategy Nash equilibrium, the pitcher is pitching a fastball half the time, the batter is swinging for a fastball half the time, and similarly with a breaking ball, the pitcher is pitching breaking ball half the time, the batter is swinging for breaking ball half the time. But of course, these are independent choices. This is non-cooperative game theory. These are independent choices. So unfortunately for the batter, they don't know. They're swinging half the time, but they don't know what half the time there is actually going to be a fastball and what half the time there is actually going to be a breaking ball. They only know the probability distribution. Okay, here's another example of a game that does not have a pure strategy Nash equilibriums, and you should confirm this for yourself. But once you confirm this, you then can look for a mixed strategy Nash equilibrium. So in this game, Intel and AMD play a chip design game. Intel is the market leader as player 1, and essentially Intel wants to design a unique chip, and AMD really wants to just go the direction that Intel is going. So AMD wants to be in coordination with Intel. But Intel doesn't want to be in coordination with AMD. They would rather have a unique chip design as the market leader. Okay, so we follow the same approach here. We calculate a P mix row and a Q mix column. And in this case, the P mix row is going to calculate the payoff to player 2 should player 2 choose strategy A, so that first entry is going to calculate the payoff to player 2 should player 2 choose A and player 1 follow the mixed strategy where they're choosing A with probability P, B with probability 1 minus P. So that payoff to player 2 is going to be, well, with probability P, they're going to guess right in choosing A. They're going to get a payoff of 40. And so with probability 1 minus P, they're going to guess wrong by choosing A, and they're going to get a payoff of only 20. Okay, so then we move over to the second entry in the P-mix row, and that's the payoff to player 2 should player 2 choose B, and player 1 follow the mixed strategy P1 minus P. So if player 2 chooses B, then player 2 is going to get a payoff of 20 with probability P, so they're going to guess wrong in this case with probability P, get a payoff of only 20. But with probability 1 minus P, by choosing B, they're going to guess right with probability 1 minus P, and they're going to get a payoff of 30. The expected value of choosing B in this case is going to be 20P plus 30 times 1 minus P. For the Q-mix column, we have payoffs to player 1 given the mixed strategy choices of player 2, Q, and 1 minus Q. Okay, so we have payoffs for pure strategies by player 1 given the mixed strategy choices of player 2. So the first entry in the Q-mix column says the payoff to player 1 should player 1 choose A and player 2 follow the designated mixed strategy. That's going to be, well, by choosing A against this mixed strategy, player 1 is going to get 60 units of payoff with probability Q and 80 units of payoff with probability 1 minus Q. Okay, and then the second entry in the Q-mix column is going to be the payoff to player 1 should player 1 choose B against the designated mixed strategy of player 2. By choosing B, in this case, player 1 is going to get a payoff of 80 with probability Q because player 2 is going to choose A with probability Q, plus player 1 will get a payoff of 70 with probability 1 minus Q because player 2 will choose strategy B with probability 1 minus Q. Okay, so we're going to set the respective payoffs in the P-mix row equal to one another to get the optimal choice of P for player 1. And we're going to do the same to get the optimal choice of Q for player 2 along the Q-mix column. Okay, and by setting these payoffs equal again, we're just recognizing that player 1 is going to choose P to make player 2 indifferent between their two pure strategies and vice versa. Player 2 is going to choose Q to make player 1 indifferent between their two pure strategies that are available. If you don't make the other player indifferent, then you're leaving an advantage for the other player, and in fact, you're not mixing efficiently. So if we set the P-mix row payoffs equal and solve for P star, we get that P star equals 1/3, and so 1 minus P star equals 2/3. If we set the Q-mix column payoffs equal and solve for Q star, we get symmetrically that Q star equals 1/3 and 1 minus Q star is 2/3. So essentially, most of the time, in this case, Intel is going to choose chip design B, and most of the time, AMD is going to also choose chip design B. So that's the mixed strategy Nash equilibrium in this case.